Hi, welcome back to this video series on cryptography. In this segment, I will talk about pseudo-random function more formally and define what we mean by pseudo-random function from a cryptographic perspective. Okay. In the previous segment, which I encourage you to watch, we talked about how many functions can be defined from an n-bit input to an n-bit output, and we learned that there are exponential number of functions. If we randomly pick one such function, we call that function as a uniform random function or uniform function. Okay. In this segment, we are going to talk about keyed functions that take two things as input. One is key, another is an input message, for example. So we may write it like this. F is a function. Keyed function means it requires a key as an argument, right? And then a message, it could be X. Okay, K is the key and X is the message. Such functions are called keyed functions, and sometimes people write it as F with the suffix or subscript K X. So these two notations are the same, at least in this segment of the discussion. Okay, I may use both of them interchangeably wherever I need. All right, so with that a little notation, let's get back to the notion of how do we define a pseudo-random function more precisely. What does it really mean by a pseudo-random function? So this is the beautiful concept in modern cryptography, and I'm going to explain to you some formal foundation and then show it to you something like a Python implementation so we can play with it and understand the behavior of pseudo-random function. Okay, so what I'm going to talk about is that a more formal definition of how cryptographers define a function to be a pseudo-random function. A keyed function is a pseudo-random function. Okay, what they define is this. They use probability, of course, and the notion of probability is carefully used as follows. So we wanted to check whether a function f with the key k, right, as a pseudo-random or not, is a pseudo-random or not. So in order to prove it is not a pseudo-random, what shall we do? We need to be able to tell something about this function f in the sense of comparing against a uniform function. So we need to be comparing fk against a random function f. Okay. If there is some difference between these two functions' behavior, then we say this is not a good pseudo-random function. So that's the intuition. So let me now precisely model this using some notations. Okay. So what we need is we need to be able to build a distinguisher D. You can imagine distinguisher as a program, which I will show to you like a program, which is given an input. Okay, an input could be, people call it oracle. So the distinguisher is given an oracle. Okay, what is oracle now? Oracle is, well, there are two things the distinguisher is given. The distinguisher is given the oracle and the key size. Okay, the key k has some size, right? 128, 256, and so on. Okay, so the distinguisher takes two inputs. One is oracle, another is number n. What is this oracle? Oracle can be either pseudo-random function or a uniformly chosen function f from the space of all functions. Okay. So what is the goal of the distinguisher? The goal of the distinguisher is to return 1 or 0, meaning it is trying to sort of decide whether the input function that you are sending it via the oracle is pointing to fk or f. Okay. Of course, the distinguisher doesn't know the key k, otherwise the whole thing is out of the way. All point, but the oracle is an abstraction. Oracle can be either fk or f. The goal of the distinguisher is to distinguish is the oracle pointing to fk or pointing to f. Essentially, that's what we are trying to do. And fk itself is a function that we would like to test. It's parameterized with the key. It need not be invertible. The fk inverse need not exist. Okay, so it's like it need not be a permutation. Okay, it's just easy to compute. a polynomial time function. The same with the D2. The D is a function that we will be writing, has to terminate in polynomial time. Otherwise, there's no point, because if you allow D to exhaustively try all possible key values, then he may be able to tell whether Oracle is pointing to pseudo-random function or uniform function. Okay. All right. With that background, I wanted to talk to you about one particular example and clarify this notion of the distinguisher. Okay. So before we do that, let me formalize what we wanted to do. We want to be able to call this function D, right? So we wanted to understand how often, or what is the probability that the function D, when we pass the oracle, say to the oracle we pass fk, right? If k is not known to D, okay, we pass the function fk and the key size of k. We are asking what is the probability that this is 1. Okay, this is the first question we are asking. And then we do the same with the uniform function. Okay, from the space of all function, we randomly pick one function, and we do the same against. We wanted to compute what is the difference between these two components, meaning these two probabilities. Okay, if the difference is negligible, what can we say? It means that the distinguisher D is unable to distinguish a pseudo-random function from a uniformly chosen function f. Okay, that's all. But if the difference between these two things, between 1 and 2, 1 minus 2, right, is non-negligible, okay, say we do it like this, right? The difference between these two components have to be bounded by some negligible function. Negligible means a very, very small number. Negligible in terms of parameterize the key size, okay? 1 by 2 power n or something like that as an example. If the difference between these two probabilities is negligible, what can we say? We can say that this function fk is not distinguishable from f, computationally indistinguishable from f. That's what we say, and that's how pseudo-random functions are defined in cryptography. So Oracle it can be either pointing to the pseudo-random function or real random function, but the distinguisher is programmed. You can imagine the distinguisher is a program. It's trying to return either 1 or 0, and we are only counting how many times the distinguisher returns 1 when it was given an input as a pseudo-random function fk as opposed to a random function f. And we measure the probability, and then we look at the difference between the probabilities, these two probabilities, and we check whether the difference between these two probabilities is negligible. If yes, we say the given function fk is a pseudo-random function. Okay, that's the idea. It may be somewhat theoretical and kind of abstract. So I'm trying to explain now with an example this notion that hopefully will clarify your comments or your questions. Okay, so how do we go about designing a system like this? So maybe we should take a simple example. Okay, what if I take my function, pseudo-random function that I'm trying to test as defined as follows. X is a message or whatever, secret. K is also a secret, of course, it's a key. And we do X, XOR K. Okay. This notation means XOR, not to confuse with exponent. Okay. I can also say sometimes this notation. Okay. All right. We are taking X and XOR it with K. And the question is extremely simple now. Is this a pseudo-random function? Okay. Is it a pseudo-random function? K itself is chosen uniformly. Okay. And X need not be, X is just a message, and messages need not be uniformly chosen. So in that case, the basic property of XOR can help us. We do know that X XOR with K, when K is uniform. This string is uniform actually. Okay, this string is uniform, n-bit string. Let's assume K is an n-bit string, X is an n-bit string for a discussion. So the right-hand side is n-bit string, and it is also uniform because K is uniform. But the question is it a pseudo-random function? Okay, that's the question we would like to disprove. that meaning we would like to prove that this is not a pseudo-random function. So how do we do that? We need to be able to construct a distinguisher D, and we need to be able to show that the difference between these two probabilities is non-negligible. Okay, so how do we go about doing that? So we can approach it like this. We will develop a simple distinguisher. The distinguisher is allowed to pick two numbers x1 and x2. Okay, two random numbers x1 and x2. The distinguisher will call the oracle. Remember, the distinguisher doesn't know whether fk was given or f was given. It's an abstract function oracle. It can be initialized to fk or f, but he is allowed to query the oracle. The oracle will be either pointing to one of these two functions, right? Can either point to pseudo-random function or real function or uniform function. So all this D is going to do is first call oracle and evaluate it at x1, and then it does the same with let's call this as f of x1, right? Or maybe f, don't confuse this with the f here. Okay, it's just I'll remove it. Let me keep it like as it is, oracle of x1, and then it does the same with the oracle of x2. Okay, x2 is another point. So what is the next thing the distinguisher is going to do? It's going to do XOR oracle of x1 XOR with oracle of x2. Okay, now what the distinguisher is going to do is that if oracle of x1 XOR with oracle of x2, this is yet another n-bit number. If this is equal to x1 XOR x2, it's going to return 1. Okay, let's reason about why is this working, or what is the reasoning behind it. The reasoning behind it is, what is the value of oracle of x1? Oracle of x1 is, let's assume for a moment that the oracle is pointing to fk. Okay, in that case, oracle of x1 is nothing but x1 XOR it with k, right? This is the definition we saw. This is the definition. So oracle of x1, let me create some room for us. Okay, so all I'm going to do is compute. Okay, so I'm going to just get rid of some old writings that I have written here. Okay, and we understood all these basics now, so I can get rid of them as well. So we can dive into the design of the distinguisher, and then we'll look into a Python program. Okay, hopefully that will clarify the idea. Okay, so all I'm going to do now is to explain to you why I'm going to explain to you why this test is good test. So what is the meaning of oracle of x1? Okay, oracle of x1, for a moment assume is pointing to the pseudo-random function, right? In that case, it's nothing but x1 XOR with k. K is the key. Okay, this is the definition. So what if you do XOR on both sides of these two equations? Let's call it equation 1 and equation 2. Okay, if you XOR these two equations, what will happen? The XOR property allows us to cancel the k because of XOR. That means the left hand side will be oracle of x1 XOR oracle of x2 is equal to, so I will write it quickly. So oracle of x1 XOR with oracle of x2, okay, is nothing but x1 XOR with x2. Okay, this is exactly what I wrote on the right hand corner, right? So the program D is just going to assume like this: oracle of x1 XOR oracle of x2. If that is equal to x1 XOR x2, return 1. Okay, so now let's reason about this behavior, right? When will D return 1? Well, D return 1 always if oracle is pointing to pseudo-random function, because pseudo-random function satisfies this property, because that's how it's defined here. This is how we define it. Okay, but what about if oracle is pointing to a uniformly chosen function f? Okay, what happens if oracle is pointing to a uniform function? So now it becomes interesting. So if it is pointing to a uniformly chosen function f, okay, let me explain how that will behave, right? So all I have to do is now show to you how often this property will satisfy the property that I wrote on the right hand corner, right? Oracle of x1 XOR with oracle of x2 equal to x1 XOR x2. How frequently that will satisfy when oracle is pointing to a uniform uniformly chosen function small f. Okay, so let's do that. So in that case, what are we trying to do? We are trying to do x1 XOR with x2. Remember, f is now pointing to a uniformly chosen function. We are going to ask, how frequently is this true? Okay, let's assume this is true for a moment, which means we can say f of x2 is equal to x1 XOR x2 XOR with f of x1. Okay. The right hand side is just a random n-bit string, right? x1 and x2 are random n-bit strings. Therefore, the right hand side is a random n-bit string, and the left hand side is also a random n-bit string, because that's how f is defined. F is a uniformly chosen function. So what is the probability that two n-bit strings are equal? That means each bit has to be equal. That means 1 by 2 power n is the probability that f of x2 is equal to x1 XOR x2 XOR f of x1. So if d is called by passing a uniformly chosen function f as an input to the oracle, d will return 1 with the probability 1 over 2 power n. Okay. On the other hand, if d is called with a uniformly chosen, let me rephrase it. On the other hand, if d is called by choosing a pseudo-random function fk, it will return 1 always, right? So the probability that d returns 1 if oracle is pointing to a pseudo-random function is 1. On the other hand, if oracle is pointing to a uniformly chosen function small f, the probability returns 1 is 1 over 2 power n. Therefore, the difference between these two probabilities is 1 minus 1 over 2 power n, which is not negligible, right? When n is very large, this is really, really tiny. Therefore, the difference between these two probabilities is non-negligible. Therefore, we say that this function fk that you're seeing here, as defined as x XOR k, is not a pseudo-random function. So we have to be able to design a d and argue why it is not a pseudo-random function. Okay. Now I will show to you a simple Python demo how I model all of these things. Okay. Hopefully you will find that informative and useful. Okay. All right. So it took me some thinking to come up with a way to simulate this, right? It's not perfect. I'm not claiming perfection, but hopefully this is valuable for you. Okay. So what you're seeing is my implementation of this this Oracle distinguisher concept, right? And I'm running it with Python version 3.8. So I have only tested on that. I don't know about other versions. So, remind me later, please. Okay. So let me walk you through some of the core ideas that we talked about, right? I'm using the Python secret module. I have set the key size to be 128-bit. And I have to model the capital F first, right? Capital F is the pseudo-random function, right? Which takes x and k as inputs. Well, as a matter of fact, I could very well put this k as argument, but I took it outside for some other reason. Okay, so don't worry about it. We can also program it like this: k inside and n inside, right? But take it simple. F is the pseudo-random function, right? That we want to test for. And the f of x is nothing but x XOR k. That's how we define the function for the pseudo-random function. Now, we need to find out a way to randomly pick a uniform function, small f, right? How do we do that? So here's the hopefully neat trick. What I modeled is like this. I used the Python's dictionary concept, right? So what I do is, you can imagine the history is starting with an empty dictionary. I populate it on the fly, meaning let me go through the distinguisher first and come back. The distinguisher is given an oracle and the key size, right? It generates two numbers x1 and x2 randomly, and it checks whether x1 XOR x2 is same as oracle of x1 or XOR with oracle of x2. If it is true, it returns 1, otherwise it returns 0. We wanted to measure how many times it returns 1 when oracle is pointing to pseudo-random function as opposed to it is pointing to a real random function. Okay, so that's basically what I did. I'm measuring how many times it's pointing to pseudo-random, how many times it's pointing to real random. How am I doing it? I'm actually creating an experiment, right? Here, and calling the distinguisher how many times? 10,000 times. And each time I am setting my oracle either pointing to pseudo-random or to the real random. This capital F is pseudo-random, right? Which we want to test. And here it is real random or uniformly chosen, okay? Uniformly chosen from the space of all functions. And whenever the function returns 1, the D returns 1, I increment the count of F by 1. Okay. All right. And I'm running it 10,000 times, and I will directly first run it and show to you. As you can see, I run it 10,000 times. In all the 10,000 times, when the argument to D, the oracle, is pointing to pseudo-random, I get 10,000 times the return code is 1. On the other hand, when I'm calling the distinguisher on a randomly chosen function F, I never got 1. No place or never this function, let me show you the function D now. D never returned 1 when my oracle is pointing to a pseudo-random function. So it never reached the line number 26. That's interesting. So now I'll show it to you, which means, by the way, that our D is a good D that is helping us to distinguish between a pseudo-random function and a real random function. Okay. But now, how did I model the real random function, so-called real random function? Okay. So what I did is actually I created a function F, right, which takes an X as an input. I check whether did I see the X in history. If I have seen it in the history, I return the value of history of X. Okay. Otherwise, I generate a random number, assign it to the history, and return the history of X. So this way, I will be consistent and correct. Remember, F itself is a randomly chosen function, but it has to be consistent, meaning when you call F with the value 5, it may give you some number. But if you call the same F with the value 5, it will give the same number. That's the reason why I have to put it in the history. And if it is not in the history, I put it in the history. Okay. This is one way for me to simulate the small f. Okay. And overall, the oracle is basically doing oracle can be either uniformly chosen function or a pseudo-random function. And we call D, in this case, 10,000 times and look at how many times did we hit the branch which returns 1. And if there's significant difference, that means we found out something is wrong with our function, pseudo-random function, capital F. That's basically what I did. I hope that you find this informative, that you can easily program this notion using a simple Python program. And the only trick is to simulate a uniform function, right? And that's the trick that I played, is create a history, which is like a dictionary. You can imagine like this at runtime, the history is like this. For a value 0, 10, for value 1, 11. So it's like a key value pair mapping kind of thing. When X is in history means it checks whether, say, let's assume somebody is calling f of 0. What it will do, it will check whether 0 is part of the first component. If it is, it will return 10, for example, in this case. So that's basically what this in history means. Okay. So at runtime, this is going to be huge, so you cannot keep doing it for a long time because the history table will explode. But I hope that I have convinced you how to design a distinguisher and how do you sort of compare whether you are given a pseudo-random function or a real random function. Of course, the challenge is to come up with this line number 25, right? The distinguisher has to be programmed in such a way that it can distinguish a real random function from a pseudo-random function. Okay, that's basically what I wanted to show to you. And then one thing you may also try, which I also tried, is suppose your function fk is as you're seeing here, like x or k. You may also use HMAC. If you're familiar with HMAC, you can substitute the f by HMAC function. Okay, and that way you can also play with this notion of distinguishing it. And I actually developed one, which I will show to you quickly. Hopefully you find that interesting as well. What I did there is, I will show to you very quickly what I did. Okay, so suppose my pseudo-random function is as it is earlier, right? But my random function is is now HMAC function. Okay, HMAC is a mapped version of a mapped version with a key. So we need a HMAC key and some data X, but the Oracle doesn't know whether Oracle is given pseudo random function FK or the other function that we would like to test for. Okay, you can run this experiment and you will find out that this test is always failing when meaning it will always reach line number 21 when our Oracle is pointing to random HMAC as opposed to the FK. That's another trick you can try and play with it. But that's basically what I wanted to show to you. Hopefully you find this informative and useful. Thank you.